Inductive reasoning is using just basically logical reasoning. You look at it, you study it, you look for patterns, and you study those patterns, and you make conclusions based on that. We're just going to do some simple inductive reasoning as we look at this. What we can do is look at patterns of data and look for common differences, common sums. Difference means subtract and sum means add. Difference products, things you multiply. Look for common quotients. Check for squares. Check for square roots. So we're going to try to look at a pattern in the data and then continue that pattern to see what is next. So if we look at from 2 to 4, say, well, that's a plus 2, and from 4 to 6 is a plus 2, and from 6 to 8 is a plus 2. So if we did another plus 2, we'd get a 10, and another plus 2, we would get a 12, and so we saw a common sum. Now, we use these in algebra as we look for common sums or differences or products or quotients as we were trying to decide whether something was linear, quadratic, or exponential. Remember, if the change in y over change in x was constant, it was linear. Or if the change in y, change in x was not constant, it was not linear. So we would check for the change in y. If the change in y was a plus, 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 or minus, minus, minus pattern, we said that it was quadratic. We would go to the calculator and put our x's in L1 and our y's in L2 and go to stat, calculate, quadratic regression. Or if the change in y was a times, 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 or divide, 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 it was a quadratic, it was an exponential. And so we could do an exponential regression. So we used this as we were doing that particular application. So here from 20 to 16 and 16 to 12 would be a minus 4, minus 4. So we could keep the pattern of minus 4 going. 12 minus 4 is 8. And the pattern of minus 4 going, 8 minus 4 is 4. And what we found was a common difference. 3, 6, 12, 24. Well, that's not the same sum. What you would do to go from 3 to 6, 6 to 12, 12 to 24 is to double. So that's a times 2, times 2, times 2. 24 times 2 would give us the next element, 48, times 2 would give us the next element, 96, and so on. And so we found a common factor or a common product. Actually, what we found was a common factor, which will result in these new products. If we go from 900 to 450, 450 to 150, what we see from the 900 to 450 is a divided by 2, but in the 450 to 150 is a divided by 3. So if we continued the pattern of divide 2, divide 3, the next would be a divide 4. So it's not necessarily a common quotient or a common divisor. It's a divisor that you can see a pattern in. And so we could then divide by 5, and 150 divided by 5 would be 30. And then we would continue the pattern by dividing by 6, and 30 divided by 6 is 5. And we really didn't find a common divisor. We found an increasingly larger and larger divisor. And so the divisor was one more than it was the time before. Okay? When you look at example 5, you may be hard-pressed for a pattern for just a moment as you check for common sums and differences and quotients, products. But then what you may notice then is 1 came from 1 square, because 1 squared is 1 and 2 came from 2 square and 9 came from 3 square. So what we have are the squares of consecutive integers. So the square of 4 would be 16 and the square of 5 would be 25. And so we have common squares for squaring, squaring, squaring. So we're looking for squares, quotients, products. Really in quotients, products, the result is a product or a quotient, but we would be looking for add-ins, subtrahends, factors, and divisors. Okay? All right. We're going to go ahead, since this was a little bit of a short lesson, and go ahead and do some of the daily work with it. And so it says find the next two numbers in each sequence. So we start looking for a pattern of how to go from 12 to 10 and 10 to 8. And we see a common pattern of a minus 2. So we would do another minus 2, which would take us to 6, and another minus 2, which would take us to 4. Any questions on number 1? Let's look at number 4. It's kind of tricky, isn't it? You may play around and go with that and say, well, that's a plus 6 and then a minus 4 and then a plus 12 and then a minus 8, and that's all kind of weird. So you think, well, let's try something else. Well, let's try a plus 6 and a divided by 2 and a plus 12 and a divided by 2. Well, the divided by 2 worked both times. So it seems like the red maneuver is a divided by 2 move. But let's try to find some consistent pattern in the black part. Well, 2 to 8 is a times 4. The plus wasn't working out. And 4 to 6 is a times 4. And so sometimes you're going to find patterns that aren't the same thing every single time, but there's two patterns going on that are playing leapfrog with each other, if you want to call it that. But anyway, you can find these patterns within a pattern there. Okay, so look for crazy stuff going on too. All right. Now, what this is some information that makes us think about what is given and what conclusion we can reach from that information. And again, just a little bit different type of reasoning approach than a formal two-column proof. So what can we conclude? It says angle 1 is greater than angle 2, and angle 2 is greater than angle 3. Now, we could logically say it like this. If angle 1 is bigger than angle 2, then we could say that angle 1 is large and angle 2 is small. Now, that means angle 2 is still small, but angle 2 is bigger than angle 3, so angle 3 must be smaller or smallest. We can conclude then that if angle 1 is larger than angle 2, and angle 2 is actually larger than angle 3, then angle 1 must be larger than angle 3, which is smaller than angle 2. So we can conclude then that angle 1 must be greater than angle 3. Inductive reasoning. Everybody see how we got that? Okay, and you can play with the others on your own. All right. That ends the daily work, which brings us in the text to odd answer solutions. Don't forget that the odd answers are there, and they are totally worked out. The odd answers are there, and they are totally worked out. And so enjoy using those to help you with problems that we may not have worked out together. We even have some proofs done. There's the daily work done. 2-column proof. We got some diagrams, draw and label. So those are in the back of the book. That's going to help you with some of those that I'm not going over. The discovery problems, notice it says the solutions are not given. That's because the solutions are actually the theorems on the next page. So all you got to do is flip to the next lesson, and there's going to be the answers to the fill in the blank part at least. I'm just going through this again so you can see that the odd answers in the back are not just answers, they're actually solutions. It's all totally worked out. And there it is through 3-7. Okay? That'll bring us to the study guide. It's a review at the end of the chapter, which is like the homework set up for the chapter, which is like the test for the chapter. So what I do in class is I go over the study guide. The students will do the homework for practice, and then I'll give them a test that looks like both. Okay? So that is the end of the recording for lesson 3-7 and its daily work. A little review of what the odd answer solutions look like, and another some more insight into the way the testing is set up.